to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause the stream is about to start. Get ready wherever you are, 'cause the stream is about to start. Hi, I'm Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is data structures for JS effects. 2 days ago, we landed on the approach that we want to use for our library. We are going to have real objects in JS effects, so you will be able to put a filter, like a low pass filter, in a data structure, like an array of filters. Cool stuff. And we are not going to go overboard and have everything be a real object like we had in the previous incarnation of the library. So today we are going to revisit every data structure, and we are going to change them so that data structures themselves are not objects, but the instances, or I should say the definitions of the data structures, are not objects. But the instances of when you're using a data structure, those are real objects. Similar to what you would have in Java, for instance. And while we are doing that, we are also going to simplify the way that you use the data structures to clean up the code in many different places. So let's dive into the library as we are reconstructing it. So this is what we have so far. It's just simple functions that don't really have any data structures attached to them. And then let's go to the bottom and start bringing some of the data structures from the previous version of the library. I'm going to skip over imaginary numbers and go ahead and talk about the data structures themselves, because imaginary numbers may be a data structure where they have a real and imaginary parts, or they may be real and imaginary variables that you pass on. I'm not really sure, because imaginary numbers actually occur in the JSFX library. We don't have a lot. When I say JSFX library, I just mean as native JSFX functions. We don't have a lot of infrastructure in JS effects. We only have bare bones things like FFTs, fast Fourier transforms, and convolution and that sort of thing. But when we use imaginary numbers with those functions, they are just real and imaginary parts. And the same thing is true of X and Y coordinates for functions that deal with graphical user interface. You don't pass a pair, which is a data structure. You pass literally just X and Y. So I'm not really sure how I will want to work with imaginary numbers. Let's go to the part where we know what we want to do. And Bo is here. Hello, Bo. Great to have you here. How is it going? Are you feeling good? Hope you are. Hope you enjoy this. Well, if you're watching from your sofa, it usually doesn't mean a good thing. How does the sound translate on a TV setting? I sometimes test my own. I sometimes watch myself after the stream on my TV, just make sure that the audio works well. But I optimize the audio for headphones. I suppose I can hear more detail on headphones, but I think it's fairly good. Wanted to know your opinion. Let's start with the... I'm going to skip over the enumeration because I feel like I may not really want to implement that. Let's see where I used enumerations. I use them to distinguish between different filter types. that could be a good thing. But let me move on to the more interesting part, which is memory allocation. Because enumerations don't really need to allocate any memory. They're just different numbers. I just need to make sure that the numbers are different. So this is very simple stuff. Let me move on to the memory functions that are actually more interesting. Oh, sorry to hear that, Bo. I really am. It's a bummer. Right, so memory. I'm not sure if I want to have a section just called data structures. I think I'll have a section called memory allocation. And we are going to still going to keep things simple and just have an allocator, but we'll not have a deallocator. So you're just going to claim memory, and I won't give you any way to free memory. Yes. Bo is telling me to check. I think that is the person who is working on the toucan effects. Am I right? Something like that. I may be wrong, but I will check this person out. Tom Coot. I'll put it here on my list of things to do. And that's great news. It's great news that more people are interested in doing this thing. That makes me happy. Right, so the basics of how we are doing memory allocation feels good to me. I'm going to copy this over, but there are some things that I want to consider. Let's see. The next available address is a global property. Oh, so it's not the toucan guy. Okay. I think I saw that name, Tom Coot, on my YouTube suggestions, but I don't really remember. Right. So this is just a global number that is the top of our memory, where we have memory available to us. And then you give me the size of the chunk of memory that you want to allocate, and I will return to you the address for that memory. So it's just doing that, remembering the old value and then returning that. But then we also update based on the size that you gave me, and I set that memory to all zeros. I am removing this mem set. If I remember correctly, this mem set was there to fix a bug, because memory was not being zeroed out between runs, and then there was junk there. But the problem is memset has a limitation. We have to be mindful of that. Memset provides the ability to quickly set a region of local memory to a particular value. Oh, interesting. I thought that memset had the same limitation as memcopy, because in memcopy you cannot have a buffer that crosses a certain boundary. But with memset, it seems like you can have that. So the limitation that I thought existed doesn't really exist. So that's actually good news, because I can keep zeroing out the memory, and that's a good thing. It's going to guarantee that you get zeros in there. So in JSFX, if you start using a variable, it will be its value will be the number 0, and the whole memory is also zeroed out to begin with. But it's nice to have this here, because if you have your init block running again and again when you play and pause or play and stop and play and stop, and you're guaranteed to have not junk, but something cool there, a bunch of zeros there. And I suppose I could have something here to give me an initial value, so I could receive an initial value and I would set that. And we had that in previous versions of the library, but it turns out that in most cases you allocate memory and then you know what you want to do to initialize that memory anyway. So this memset is more like I guess it's necessary, it's a safeguard, but most functions that use this should initialize memory themselves as well. Now, there is something else that I want to add to the memory allocator. And that is the notion of alignment. Coming back to the issue I just mentioned, there are some functions that have this restriction, and in particular, the FFT functions. So if you just look for this number, you're going to find a couple occurrences. So the discrete cosine transform, the fast Fourier transform, and convolution, as well as memcopy that I just mentioned, they all have this restriction of item boundaries. And I suppose that is because performance, right? There must be a performance reason for this. So this number is a power of 2. I forget what it is. It's log 2. It's 16. It's the 16th power of 2. So I bet that this is here for performance reasons. Like if I want to calculate FFT, then powers of 2 become important. So I will have a different memory allocator. Usually you want to use this one, but if you know that the memory you are allocating is supposed to be passed as an argument to one of these 4 functions that I mentioned, discrete Fourier transform, fast Fourier transform, or discrete cosine transform. The discrete Fourier transform is another thing. So discrete cosine transform, or FFT, or convolution, or memcopy. If you know you're going to pass memory to one of those functions, you need that memory to not cross one of the boundaries. That's what this other function is going to do. A variation called memory new aligned. And I couldn't have another parameter here, but this is such a niche kind of thing that I prefer to have it as a separate function, though the body of the function will have some similarities. So you give me a size and I will return you an address. And oh, you know what I just realized? There is a cooler way of implementing this. So check this out. To begin with, I'll just call the other memory allocator. But I will do a little trick just before I call the other memory allocator, which is to change the number in this variable if necessary. So the strategy is going to be, I'm going to check if I need to, I'm going to check if I can allocate a memory chunk of this size without crossing a boundary. If I can, I will not do anything, I'll just call memory new. On the other hand, if I cannot allocate a memory chunk of this size without crossing a boundary, I'll change this number to be right after the boundary, and then I will call the memory allocator just the same. So that's the strategy. So how do I test for this? I guess I can use logarithms for that, right? Yeah, let's draw a little diagram here to help us reason about this. So I'm going to call this the boundary. And let's say that the boundary is the number 5 instead of being this big number. It always helps to think about smaller cases. So here is a little bit of memory, just like that. And let's say that we have already allocated, or maybe let's say that we have not allocated any memory. Oh, I guess this was supposed to be a 0. I guess you can see what I'm doing here, right? So this is the first digit and this is the second digit. And these are memory positions. So to begin with, the cursor will be here. We have not allocated any memory yet. And let's say that we want a size of 3. Then what is going to happen is we are going to plus that size, 1, 2, 3, and we get there. So that's a little pointer for the next available place in memory. So if we are at 0, 0, let's draw another thing. Let's draw another thing to help us visualize these boundaries. So the boundary is a size of 5. So I'll have boundaries in these locations. No, that's one more than what I should have. And when they say the boundary, I am not really sure if when I allocate a chunk of memory, if I am able to do this or if I am able to do that. Their documentation, as far as I can tell, is ambiguous. So I am going to be on the safe side and not allow for any of these two. I will not allow anything to touch the boundary. Not to one side, not to the other side. I suppose because everything is 0 indexed, I suppose that this is their intent. That you are able to put things right on top of the boundary, but not on top of and after the boundary, but not on top of and before the boundary. So I think that crossing the boundary is right where my little blinking cursor is right now. I think that's what they mean. But just to be clear, I'm going to keep it on the safe side and I'm not going to touch that position in memory if you want the memory to be aligned. Which worst case scenario means that you will not be able to allocate this many items. You'll be able to allocate one fewer, which is fine by me. For most purposes, it's fine. In fact, if you think about it, the maximum number that we can have for an FFT is this one. Oh no, I need a chunk of memory of that size if I want to do the maximum FFT. That's too bad. So let's go with my intuition that this is their intent. So how do we first calculate these boundary points? Well, we can take, let me put some space here before, because I want to write some things. These are like my items or my chunks of memory. Well, these are addresses. So how do we detect these boundaries? Because there is another boundary here, right? How do we come up with an equation to calculate where these lines lie? It's actually super simple. You just take the address and the result of the division by 5 and check if it's equal to 0. If it's equal to 0, then this is a boundary. And this is not, because the result of the division between the address and 5 is going to be 1 and 2 and 3 and 4. And then the result of the division of 5 and 5 is going to be 0. So in that case, we are at a boundary. Right. So that's how we compute these things. Now we need to compute whether we are trying to do something that looks like this, where we are crossing the boundary. Well, let's say that this position over here is the A stands for available. Or maybe this is the start and this is the end. So what I need to do is to check if the start is in one chunk and the end is in another. Because in that case, I am crossing the boundary. And one thing that I probably could do, maybe even I should, but I won't, is to check that the size you're giving me is less than this size. Because if you're trying to align memory to this size and you're asking for more memory than this size, what are you trying to do? There's no way I can fulfill that request for you. So I'm not going to test for that. I'm just going to suppose that you are doing the right thing, which is, I guess, a theme that we have been developing in this library for a while now. We tried to have more systems in place and checks and that kind of thing. Turns out that checking for the boundaries of everything is expensive, so you don't want to do that. So I won't try to prevent you from making the silly mistake I just described of asking for more memory than can be aligned. So how do we check in which of these boundaries we are? Again, I guess it's super simple. Just take the division by 5 and the floor of that. Not the flute, the floor of that. Because it starts as 0, 0, 0, 0. When it gets here, it's going to be 1. So that's how we check in which of these boundaries we are. Let me write it here. So this is going to be like boundary 0 or region 0. Yeah, I'm going to call this regions. Region 2, region 3, and so forth. Okay, that looks reasonable. So yeah, let's see how we can actually do all the tests that we need over here. So I'm going to check if this next available address, and I'm going to check where it is in terms of region. What is its region? I'll use the formula on the last line here on the page. And of course, I won't divide by 5. I will divide by this number, which is the size of my chunk of alignment. If it is not equal to the end, right? So our S here, our start is this, and our end is, let me just make sure. For instance, in this case, our start is number 3. That's where we currently have our next available address. So 3 would be this number in this example. And then the floor of 3, I'm going to say divided by 5, it's going to be 0. So our start region is 0. And how about our end region? We are right at the boundary, so the end region should be 1. And I'm using this formula, so let's check that formula. It's going to be 3 plus size, which is 3. So that is going to give me the number 6, which is not this number over here. So I need to subtract 1. And I guess that's a consequence of indexing everything by 0, because then this will be equal to the number 5. And then I divide that by 5 to have a 1. So I am in this region. So yeah, if I start at position 3 and I want to allocate 3 elements in memory, 3 items in memory, I will use items 3, 4, and 5. And to get to the number 5, I have to subtract 1, just like that. So if these are different, then I know that it's not aligned. And in that case, I need to update this. And I am going to update this so it lands here on the number 5 in our example. And how do I do that? Well, I'm currently on number 3. So I guess I take the ceiling of address divided by 5 and multiply by 5. I guess that's going to work. Let's check. So if I take the address, which in this case is going to be address 3, and divide by 5, I'll have 0 point something something. The ceil of that is going to be 1. Multiplied by 5, I'll have 5. That sounds right. So I want plus equal. I will just use this formula, but just like that, and this. Now, I don't like how this number is repeated all over the place, so I'm going to say that this is the memory alignment size. Probably there's a technical term for this thing, but there you go. Now this doesn't look all that great, I don't think, but it will do. Okay, so I'm going to commit this, though it doesn't really work. Now it works. Okay, I'm going to commit this and we're going to test things on. Maybe we write some tests for this. Yeah, let's write some tests for this. I was considering maybe just testing things interactively by hand, but we have already a test suite here, so why don't we use that? And this is going to be, I guess, underscore memory. I'm going to test everything about memory in one place. So let's start with the easy stuff. I'm going to check that that starts at 0. And that when I try to allocate, Aria is here. Hello, Aria. Great to have you here. And you look different. You're not on your IDDQD account. So if I try to allocate 5 positions, well, I really want this boundary to be 5 so that I can work with these examples. So I guess that's what I'm going to do. I am going to set the memory alignment to be 5 real quick. And then I'm going to reset it after the test. Right, so if I allocate 5 places in memory, you don't want to expose your real face to people. Right, so let's allocate 3 pieces of memory, 3 items in memory, and the result address should be the address 0. And we are not dealing with aligned allocation. IDDQD sound is here, not Aria. So memory alignment is not an issue here. We can get address 0, and then when we allocate 3 more items, we should get address 3, right? I just allocated 1, 2, 3, so the next will be at position 3. Great, all of that makes sense. Now, let's try to allocate with memory alignment. So right now we are in position 3, which, look at that, is exactly our example. So if I try to allocate 3 more elements, then I should not get oh, hang in there. No, I already allocated more. I'm already at 6. Right? So I expect next one to be the number 6 because it's right here and it is aligned. So I expect it to be the number 6. But if I do one more, then we are here at 9, and that is not correct. I should expect to see 10 instead. And I think that about wraps up the tests, because this is not going to be the number 9, it's going to be the number 10. And it kind of reads nice. 0, 3, 6, and you would expect 9, but you see 10, which makes this stand out, the fact that it's aligned. Okay, let's see if we got this right. Memory, pass, we got it. Hooray. And just like that, memory alignment. Cool stuff. You're probably not gonna need this often, but when you do, it's there. And we did it from first principles. I always like when we can work things out from first principles and get it right on the first try. It doesn't happen that often. Right, so next, let's look at what is next. And you have this thing here where it's just a box. I'm not really sure I love this idea. Yeah, the only place where you use this is to define structs. And I feel like if you have a box, you might as well just use a variable. So we're not going to implement the box right now. I guess it goes in the same bin as the enumerations. We'll see if we want that. Then structs, I guess, is something that we don't want. We want the structs to not be values, because that complicates the code a whole lot. In fact, the first simplification that we are going to see that stems out from that is the fact that we no longer need to initialize data structures like that because they're going to be fixed. We don't need to allocate them in memory. So the definitions of the data structures don't need to be data structures in and of themselves. So let's do something to let us define array. So the difference between just a chunk of memory and an array is that an array remembers its own size. And I mentioned this idea before. The way that we implement this right now is we have a data structure with 2 positions. But that's kind of silly because then in memory, an array looks like it has 2 positions, right? So it's a struct. I'm going to define a struct like this. It has a size and data. And the indices into the data structure are this. And then the data is a pointer that points to a list. And that's the chunk of memory that we actually store data in. So here are your good old numbers, your data. But the silly thing is that this allocation is going to happen right here and then right there. So I know for a fact that the address that I have here, so if the first thing I have in memory is an array, so this is going to position 0 and 1, I know for a fact that the address of this chunk of memory is guaranteed to be 2. So I am storing the address of essentially the next location. The data here is a pointer pointing at the number right next to this one. It's wasting resources. It's making us do more memory lookups than we should have. And it is going to, well, use one more item in memory. It's just a silly concept. Doesn't have to be that way, right? So how about we just shift everything? And then you don't have to access an array data using this field in the data structure. You can just say array in position 2 and you get this element. Makes a lot more sense, makes the code simpler, makes everything faster, fewer memory accesses. It's just better all around. So that's what we are going to do. We are going to tuck away the extra data, or the metadata, and negative indices, which I think is a smart move. It does not reuse the data structures so neatly as we did here, but it's much simpler to use. So I'm going to go with that. And all you have to do is give me a size, and this is going to be the function that allocates an array. So maybe I don't need the .new, right? I used to use this naming convention where I put .new in front of everything. I don't quite need that. Yeah, let's just get rid of that. And it's even simpler to declare an array. Cool stuff. And we are using the underscore as a namespace for everything in our library because there are some variables like this that you don't want to see on the top of the little pane that shows all the variables in use. That's why I have the underscore as a prefix, because underscore sorts last. And because of that, we sort of have this convention where underscore dot array is to create an array, and a variable, which is an array, can be called just array, which is really super nice. So how do you define an array? Well, I need to allocate memory, so I'm going to say just memory of that size, and I'm not going to deal with aligning arrays, okay? If you need align memory to do some other things, then there won't be an array data structure for you to use. You have to remember the size of your stuff yourself, at least for now anyway. So this is just the chunk of memory that I'm allocating, but I also need one more position for the size. So I will have something here called array.size, which will be index -1. And then I return array +1. So in order to make things simpler to use, as I am explaining, I'm sort of making things harder to, I'm going to say harder to write for myself here, because this is something that is kind of weird. I'm taking an address in memory and I'm doing arithmetic to that. It's something called pointer arithmetic in languages like C, and it can be confusing. So it's a powerful thing that I'm doing here. I'm treating addresses as, well, essentially data, and I'm doing arithmetic with that. But in most cases it works, so yeah. Right, so really this is all I need, so I might as well just inline this here and not have a local variable at all. And yeah, essentially I guess I'm just offsetting this memory by 1 to hold the data, or to hold the size. So let's write some tests to actually drive home the point that this is going to be simpler to use. Let's write some tests for memory. I'm going to, or not for memory, for arrays. I'm going to put this up here so that it reads nice. All the sections are like that. And then what I'm going to do here is essentially copy one of these sections. This is going to be array, and I will have the parentheses there as well. So let's start by allocating an array of 5 elements, and let's put stuff in there. You know what? Tail taught me of a function that we could use here. It doesn't seem to be documented though. Memcopy, memset, memtop. Yeah, it's not documented, but there exists a function that does lines like this. I'm not going to complicate things further, so let's just do it like this. And then we can write the tests for it actually. So I expect the size to be 5, and I expect... Now this is kind of silly. I'm setting a value, I'm reading the value, but I guess that makes sense, right? You get my point. And let's see if this bad boy is passing. No. We are using memory.new over here. All right. Let's give this another shot. And then the array is failing. Interesting. Let's see why. I'll go and edit the code and see how our variables in the test effect is above all the other ones. Cool stuff, right? So let's see why this is not passing. What do I have over here? I have 100. This is 100. And what is that? That's a 0. Oh, of course it is. I should set... I guess I'll call this an address. Because it's not really an array, it's more like the address of the array. And right at position. Or maybe I'll call this an array. And I will do it like this. And now this should be passing. And it is. Great. I was forgetting to actually store the size of the array in the array. But now I'm getting the array, which is this offset memory kind of deal. Then I'm storing stuff in the negative position and returning the base address. And then over here, I'm indexing into that negative position to get a hold of the size of the array. So I find that this is much simpler to use than having to write something like that. What do you think? I think this is a lot better. All right, let's do one more. Circular buffers are complicated. Arya says, I got tons of catching up to do before this makes sense. I suppose. And I can summarize what I'm doing. I am making data structures that are in the sweet spot of being relatively easy to use, relatively fast, relatively flexible, but not super fast, not super easy to use. Because what I found is that if you try to optimize too much for one of these properties, the other ones fall too far behind. If you try to make your code as fast as possible, your code is going to be unmaintainable. If you try to make everything super abstract, then it's going to be too slow. And if you know what I mean? It's just that. So I think that I found a sweet spot by lots of experimentation. In the previous streams, I wrote a JSFX plugin that had tens or hundreds of thousands of variables. I wrote a plugin that had, I guess, 1,000 or tens of thousands of filters, low-pass filters in a cascade and that sort of thing. And I found a style that I think makes sense. And now I'm revisiting all the functions in the library to implement that style. Trying to find something relatively easy for me to do here. Maybe the filters would be relatively easy. Colors would definitely be easy. So I guess I'm gonna save that for tomorrow. And waveform stuff. Oh boy, we wrote 2,000 lines of code for the library already. Man, we have a lot here. Oh, let's have these. This is easy. These are just constants. No, let's not go there. Let's try to do one more data structure real quick. You're saying version 2 of the library? No, it's more like version 3 because we tried something else before that I forget. And then we tried JSFX, which was this other approach of writing programs that would generate JSFX. So it's more like version 4 at this point. But I think we are converging on something really nice. It's unlike any other library and it holds water. We stress tested. We know that the performance is going to be not optimal, but not horrible either. You know what? Every other data structure that I look at is kind of complicated. So I guess I'm going to call it a day because in 10 minutes I'm not able to write any of these complicated things like the filters. And tomorrow we're gonna get here and do the numbers. These numbers. Because they're easy. The colors and the spacing and all of that. And I suppose we may allocate memory, so it mostly will be just copy and paste. And we may even visit the rest of the design system that I left behind because we didn't implement everything. So we are still missing some properties that are essentially copy and paste. So tomorrow will be a chill stream where I just go over the rest of the design system and port it over to this final version that really, I think we're converging on something super nice. So I think that this is going to be the strategy. So yeah, thank you all for being here. I look forward to seeing you again tomorrow. Enjoy the rest of your day, and I see you.